Welcome to the Astronomy Club of Tulsa. I'd like to welcome you to our February 16th Arctic special. For Mardi Gras, New Orleans had a crisp 24 degrees starting this morning. I don't think they did their usual costumes down there. We'll have to watch the news sometime. But I'd like to welcome you to our club. If I can get this little thing out of my way so I can see what I'm reading. We are delighted to have you join us this evening. Our members have many wonderful opportunities to share observing the beautiful night sky, which was very beautiful last night, but I only peeked out a minute, and make some new friends and lasting memories for themselves and families. Plus, there's also opportunities for public outreach to get others interested in our hobby. Feel free to ask questions, offer suggestions, or volunteer to help at our events. All new ideas are welcome, and we're glad you're here. This part is usually done by our president, is Tambra Green, but her husband works outdoors, and today they had to continue to finish their route, which of course went rather slow. So she said she's going to try to get in later when they get home. But these are our events. As those of you who are members know, we've been holding members only observing nights at our observatory, which is near Mounds, Oklahoma, about 25 miles southwest of Tulsa. And we do social distancing and try to, stay with our groups. This year, we've just been doing them on Saturdays because of the difficulty of getting it open during standard time. But daylight savings time was resumed next month. So we'll go back to having the Friday night as our main night, because then we won't have to start until 7:30. And then Saturday can always be a backup night if the weather knocks us out. Well, we have one on March the 6th, and that one might be a special one. There'll be an article in the newsletter. That is a good night to see flares of the geosynchronous satellites. Those satellites that beam things down from 22,000 miles up. There's certain times a year when they're lined up near the equinox that they get bright enough to see in smaller telescopes. And so Brad Young, one of our members who specializes in satellites, is going to have an article in the newsletter. And hopefully, if the weather's good, he'll be out there to help us do that. Daylight savings time returns on the 14th. Us astronomers are not too fond of that because we have to stay up late for it to get dark. Our next Zoom meetings are 23rd. And then we'll have our Zoom meetings, our observing nights in April, as you can see there. Observing nights, we set up our equipment. Everybody has their own car, so we kind of set up around our car and kind of stay in our family groups or whoever you came with. If you bring your children, we're glad to have them there, but you keep them with your family, or if you do go to another group, you should go with the child. We'll wear our masks just to keep everybody safe. Some of us had inoculations, but still, it's wise, they say, to wear a mask. Sharing of equipment, you can ask the owner what their opinion of that is. That's the main reason we're not having public nights, because we just don't know what can happen on those things. We do have a restroom. Be sure and wash your hands, of course, when you're in there. The classroom has a heater, so you can warm up in there, but please wear a mask when you're in classroom. Our dome scope is not open at this time, but hopefully we'll be able to open up sooner. And just trying to have observing guidelines that let us get out in the dark skies and still keep each other safe. So I want to mention the Mars Perseverance rover is landing this Thursday. It's going to be on NASA internet program live. I also noticed that PBS, our public broadcasting station, is going to have coverage of it. I sent out a schedule to our email group, or you can just go to this website, nasa.gov/NASA Live, and there's a whole schedule of things that start tomorrow. Well, they started today, actually. They have some for elementary level, middle school level, high school level, some press briefings, and all of that sort of thing. In order to land this thing, it's pretty good size. The Mars atmosphere is so thin, they can't use parachutes to completely slow it down. So they have this thing they call the sky crane, which is essentially a rocket-powered hovercraft that comes down close to the surface and then lowers the spacecraft, the rover, on down to the surface. We used this on the Curiosity rover a few years ago, and it worked well. This one's going to have a better landing terrain imaging system, so it can zero in on its target closer. They're going to land in Jezreel Crater. I hope that's the way they pronounce it. It's 28 miles wide. For us who live around here, that's about the distance from Jinx up to north end of Owasso or so. NASA says it's about the size of Lake Tahoe. And you can see that this thing is in the middle of what's obviously been an ancient river delta, an alluvial fan where waters come down and spread out the silt. And, well, the crater is right there. It would be a good place to look for biosignatures of microbial life. You know, it would be nice if we actually found some microbes, but we might also find byproducts that are indicators of life. So that's one of the main missions of it. It has some microphones on board, so that we're going to be able to listen to the sounds of Mars. That might be interesting. I hope we don't hear the Martians talking back to us. But anyway, that of course is a false color image. It's not that color. And the other thing they're going to do is a number of experiments. This one is called Moxie, Mars Oxygen In Situ Resource Utilization Experiment. Ooh, that's a mouthful. Anyway, they're going to extract oxygen from the Mars atmosphere. Mars is made, atmosphere is like 97% carbon dioxide. And so, and it's, like 1/100th of the Earth's atmosphere pressure. So according to what I read about this experiment, it has to compress the gas down to what would be our atmospheric pressure, and then heat it up to 800 Celsius. That's pretty hot. Then it runs through an electrolyzer called solid oxide electrolyzer that's going to split the oxygen and carbon dioxide, the oxygen off the carbon dioxide, take one oxygen off, make it into O2, which will leave behind carbon monoxide. The idea here is to prepare the way for human exploration of Mars. Of course, we're going to need oxygen, and carbon monoxide, when it's recombined with oxygen, will quote unquote burn. It will release heat, so we could use it for a fuel. I don't know whether they could use it for oxygen rocket fuel, but I've read that in the past. Might be something we could do at some point. Anyway, it's a demonstration experiment. Let's see. Yeah, there it is. The other thing they're going to do is they're going to take drilling samples, store them in little sealed tubes, and make a cache of them so that at some point in the future, another spacecraft can come pick those up load them into a small rocket that can go back up into orbit, rendezvous with another satellite, and return them to Earth. We can do a lot by remote imaging and such, with our sensors on the rovers, but having them right there in the laboratory would, it's like the moon rocks that we have to examine. You can see them much better. So that's going to be an interesting experiment to see how that all goes along. But my personal favorite is the Mars Ingenuity helicopter. This will be the first time we've ever flown something on another world. It's small, only weighs 4 pounds, and stands about 1.5 feet tall. Its rotors have to be really big, 1.2 meters, 4 foot in diameter, and they have to spin really, really fast, 2,400 to 3,000 RPM. And it's going to go up as high as 16 feet and travel as far away as 160 feet. So I'm going to try to run a piece of this little video here. This is a demonstration concept to see if it'll work. Now, let's see if I can get out of this and go to my all these fancy things I don't know how to do. Here it is. Can you see that on the screen?
No, we're still seeing your PowerPoint show. Maybe it's on a different screen.
Yeah, you may need to reshare.
Okay, I'm going to stop share. Share screen. There we go.
Yeah.
Okay. Okay, this is about 3 or 4 minutes. There's a little helicopter. It's in a chamber that has the pressure reduced down to what the pressure would be on Mars.
In the same way, the Mars helicopter is designed to show that we can fly.
Are you hearing that?
Yes.
Yeah.
Our helicopter flight in the Martian atmosphere.
From day one, this was the unwavering dream of our team, to get our helicopter launched to Mars so that we can get the opportunity to do the very first rotorcraft flight test in the actual environment of Mars. It's extremely difficult to fly at Mars because atmosphere is so thin compared to Earth. At Mars, it's less than 1%. So the first and foremost challenge is to make a vehicle that's light enough to be lifted. And then the second is to generate lift. The rotor system is just spinning very fast. 2,000, 2,200, 2,400, 2,600. We're spinning between 2,000 and 3,000 revolutions per minute, and it takes a lot of energy. So it's that balance of a very light system, yet having enough energy that's needed to spin the rotor so fast to lift, and on top of it, having to design in the autonomy.
It has to be fully autonomous from the time it takes off to the time it lands. What we do on the ground is we plan the flights, and so we determine from here where we want the helicopter to go.
Our experiment window is 30 Martian days. So we have planned up to 5 flights of incremental difficulty.
The very first flight, the main thing is we want to get the legs off the ground, and so we will basically go up about 3 meters, and we'll hover there, and then we'll come down again. That will be the first, really major milestone.
Most of our flights will be at the 3 to 5 meter height. We will be going horizontally again at a few meters per second, probably go out 50, 70 meters and come back. In successive flights, we'll probably push that further, try to go further. So our priority will be to get back engineering telemetry and not so much images, but I'm sure we'll return a few, because they'll always look cool.
At this point, we've tested all we can on Earth. We have mathematical models that shows how it will fly at Mars, and we've tested it in the simulated environment that we can create on Earth. It really is time now to do the real flight test at Mars.
Nothing is a given, but we have done everything we can in terms of a test program here. The vehicle's performing extremely well so far. It's been doing exactly the right thing we would right now and is bolted onto the Perseverance rover. So there's a very good chance that we'll pull it off, yes. But it's still high risk, and none of us forget that we could have a glitch that, could be an end of mission, yes.
It's going to be exciting, reacting to any surprises we have. We can't wait. What's really most important is everything we're learning here is for the future rotorcraft systems that we want to introduce into space exploration.
All right.
Sometimes you have to do something just to show that you can do it. When the Wright
Sorry.
brothers flew for the first time, they flew in experimental aircraft.
Now, let's see. I share again. Can you see that?
Yep.
Yep. So I think that's really cool. All right. Sorry about my coughing. Well, we've already talked to our guest speaker a little bit, and I can't get my little thing to work, so I'm just going to use this screen. Our speaker tonight is Tom Field. He has his own company called, how do you pronounce that? ResSpec, real-time spectroscopy. And he's going to tell us all about how we can, what we can learn from the spectra of stars, and show us how we can do that ourselves. And I understand you're going to have a Q&A afterwards, Tom?
Yeah.
So mute our devices while we're doing that. I'm going to stop share and turn it over to Tom.
Great. Thank you, John. And by the way, thanks, John, for the work you did to make this happen. It's one of those background roles to, people don't realize all the emails that get exchanged and the scheduling and discussions and so forth. So again, I appreciate it. It makes the club a great place when you have speakers arranged like you're doing. So I'm going to speak for about 50 minutes, and then we can do the Q&A. Let me share my screen here and we'll get started. Just a second. Okay, let me just get some things arranged here and we'll be on our way. There we go. So John, shake your head. Yeah, you can see that prism on the screen?
I can see it.
Oh, I can hear you still too. Good. Okay, great. Love your logo, by the way. So how have we managed to discover so much about the universe when, we really haven't even left home? We're just right in such an immediate vicinity of Earth, all the explorations we're doing. We can get images, of course, in 2 dimensions. We can get fleeting glimpses of a 3rd dimension when we have eclipses. And if you wait a while in the time dimension, you can see there in the upper right-hand corner, it's a good place to see it. You can see some stars changing in brightness. Those are some standard candles that we use. And if we spread the colors out, we get an as-if 5th dimension. This is the spectrum that is produced that we'll be talking about, how we produce it and what all those gaps mean. And these gaps are like a barcode, and they can help us understand a lot about a star. And I'm not going to read through this list. I may refer back to it in a little bit. All sorts of things, and I'll show you examples of these tonight. Now, I think a lot of people, when they think about spectroscopy, think, oh, that's a rocket scientist kind of activity. I want to assure you that if a knuckle dragger like me can do it, it doesn't require a PhD or undergraduate degree in science. By the way, I used to have a slide with a lot of bullets showing what I wanted to cover tonight. This isn't that slide, but it was too lengthy and nobody cared anyway. So what I've done is I've got this little ding here. And when I come to a point in my talk where there's an item that used to be on that slide that I think is important, I'll share it with you. And in fact, one of the ding moments is, even for tonight, you may not be an imager, you may not be an observer, you may just be an armchair astronomer. Don't even have your own telescope, perhaps. Even then, I think that you'll find in my talk you'll learn and appreciate just how powerful spectroscopy is. In my next life, I'm going to choose a field that has a word to describe it that's a little easier than spectroscopy. It's a mouthful. So just a little bit of history to get everybody to the same level. Sir Isaac Newton discovered that you could split light in a prism and go from white light to the rainbow. And in fact, while I've got my mouse up here, because Microsoft doesn't make this a sticky option, every time I start my show, I have to remember to do this, and I usually forget. So you can also bounce light off a finely lined surface like that DVD there, or even through a finely lined surface, and that's what we'll be talking about tonight. So this guy Bunsen, many of us are familiar with his name. He invented the Bunsen burner over here to burn a sample, pass the light through a prism, and look at the result. And he was amazing. He was a pyromaniac. He burnt everything he could find. And the great thing is he kept a catalog. He would burn something and then record in the catalog what kind of rainbow he saw and what kind of gaps were in it. And we'll talk just really briefly about this friend and colleague of his, Kirchhoff. The one thing I wanted to show you on this slide here is you'll notice that some spectra are a rainbow in the background with dark lines, and other spectra, like this one, have gaps. Now, which one you get, whether you get an absorption or emission spectra, depends on things we won't talk about, temperature, pressure, stuff like that on the star. We need to get into that. And this is a ding moment here also, because you just heard me gloss over something that's pretty intrinsic to spectra, and that is, why do you get gaps versus lines? But I think one of the things that I've learned in spectroscopy is I don't have to know everything. There's that great expression. What is it? Don't let the perfect be the enemy of the good enough. There's really no reason for us to become astrophysicists to do this kind of stuff. There's a lot of interesting things that take just a minimal amount of time and skill to study. So here's some of those spectra that Bunsen might have seen when he burnt different elements. You can see, like this is the helium, for example, like Ruby and Abe. This is, if you went to a flower shop, I assume they were open last weekend on Saturday. Maybe your father went to a flower shop to get some flowers for your mother for Valentine's Day. Maybe he got a couple balloons. And those balloons are often filled with helium. Now, if he had safely found a way to drain those balloons and burn the gas that's in them, and you looked at it through a prism, you would have seen a rainbow, a gorgeous rainbow going from red to blue, but there would have been these bright lines in it. But notice that if he burned hydrogen, it would have this line that doesn't exist in helium. These really are fingerprints. It's like CSI on TV. We get to study and learn things about objects that we're examining with the rainbow. Now, hydrogen is very common in the universe, so we've given the lines in hydrogen this name, and even given them further names, these Greek letters, much like we do with the stars in the constellation. So, for example, this line, what's that color? What would you call it? Maybe robin egg blue, okay? That's our hydrogen beta line. Doesn't exist if you burn helium. So real quickly, for those of you who are familiar with the periodic table, you can see an example here, similar to what I showed on the previous page. Here's your hydrogen. If you burn it, there's the spectrum red, hydrogen alpha. There's that robin egg blue, hydrogen beta, and so forth. Very different than helium. So we don't have to burn things anymore. These days we've got, in fact, I've got one over here. This is just a gas tube. You can see there's a little, it's like a fluorescent lamp, and it just pops in there. This happens to be one, they're labeled with whatever gases. So it's a lot easier than it used to be when Bunsen was burning stuff in the 1850s. Okay, let's get this back. And I created for teachers some years ago with my software as a tool, this little camera that educators use in the classroom to look at gas tubes. It's really popular. And by the way, I meant to mention that it's been a while, but my in-laws lived in Tulsa. They lived over in, what's the name? Inverness, some sort of retirement home over by the Tulsa Hill Shopping Center. I'm looking at my map right now. It's a beautiful city. And of course, we went to the aquarium and had a great time. So a wonderful town. So So far, everybody I've mentioned have been old white men. Let's look at some people who aren't that have made major contributions to the field. So here, Annie Jump Cannon and her team, they were called computers about 100 plus years ago. They were prohibited from getting access to the Harvard telescopes because of their gender. So they ended up studying these glass plates here that are the photographic plates of spectra, and they were really good at it. They classified hundreds of thousands of these little colorful rainbow spectra. And with their deep experience and understanding of the field, they came up with a star classification these women did as a team that actually worked, unlike all the previous ones, and helped us understand the stars. Priyamvada Nataraja is at Yale, and she studies hyperactive black holes. Nancy Grace Roman was the first astronomer at NASA. She got her PhD in the late 1940s. And there's the Hubble Space Telescope in the background. She was a big, big proponent of it, helped make it happen. Elisa Quintana studies exoplanets and has discovered some planets around red giants that are just the right distance that they could have water, and maybe ET. Maybe we'll find ET on one of these. And finally, Jedediah Eisler is at Dartmouth, and she studies the gravitational lensing around black holes. So this was a fun slide to put together for me because I discovered so many other non-white men who were doing fantastic work in the field. So we've come a long way. We have a long ways to go in those kinds of equality issues, but it's a good slide for us to all keep in mind. So what tonight I'm going to talk about is the star analyzer grating. It's just a little 1.25" grating that you thread onto most any camera. Here you can see we've got it threaded onto a DSLR with a little thread adapter that we also sell. The grating's about $200. I think the adapter is about, what, 30 or 40 or something. You can put it on any sort of fits camera, cooled, uncooled. I use it on a ZWO camera like this one. It's a color camera, and it just screws, the grating just screws right onto the nose piece. You can see it there. I like the video because it's real time. So it helps me get things adjusted right. I don't have to snap a photo and then take a look at it. And then finally in the corner down here, just to show you, you can mount these things in a filter wheel. So you can piggyback your DSLR. In fact, you can actually use a DSLR standalone. There's the grating, even without a tripod. But without a tripod, it's challenging because, of course, the stars are moving in the sky, and even finding things, especially with the small aperture, can be a challenge. But it's doable. So, okay, I've raced past that, and we've got the history, some of the theory, and the equipment. What can we actually do? So we take the starlight and pass it through the grating, right, by mounting it right on the nose piece of our camera. And this is what shows up on our camera. Some of the light goes straight through. That's just the star. And some of the light gets bent into that rainbow that we've been talking about. Let's take a look. Now, this is a series, isn't that pretty? A series of spectra of different stars. Torsten Hansen captured this with just an 8-inch telescope and an imaging source video camera. And this is one of those ding moments, because I think some people think, oh, I need a mountaintop telescope and, you know, a huge aperture and some expensive camera. No, just video and even a 4 or 6-inch telescope. APO, it needs to be low chromatic aberration if it's a refractor. But you know, Celestron C8s all the time, Newtonians. So each of these are different stars, and they're in temperature order. So these are the hot B stars, and these are the hot M stars on down. There's an A star like Vega. So let's just look at 2 quick examples here. First, look down here. You see those? Well, those aren't even like lines. That's like a forest of lines, right? And they call that a band. And what astrophysicists tell us, the professionals tell us, is that when the light goes through a relatively cool gas as it leaves the star or a planet, most of the complex molecules get burned up. But these type M stars, I've lost my mouse here, these type M stars are cool enough that there's some molecule that's complex and produces a band, not just the lines, but band. And that, it turns out it's titanium oxide, but honestly, I don't know anything more about it. I do know that cool gases on cool objects produce bands. Now, the other thing I wanted to show you on this, look at this column right here. Notice that this band is the darkest and widest of the others. This is like Vega, a type A star. But these up here aren't as wide or dark, and nor are these, and there aren't any down here. So clearly, something's going on related to temperature on this. And I mentioned earlier, that's one of the key things that we do with spectroscopy, is measure, you know, if I had a candle, just a reminder, some of us are aware of this, and we look closely at the flame, the yellow part of the flame isn't as hot as the blue part. And so even here on Earth, we can tell temperature by the color, and the same thing goes with spectrum. A quick review of how these lines are produced. We're not going to get deep in this, nor is it necessary. But you know, the Bohr model of the atom, of a hydrogen atom like this, has electrons in numbered shells. Like here's one in shell 2, just going about its merry way. Sometimes they jump up to a different shell, like from shell 2, in this case, to shell 4. When that happens, when they jump up between 2 and 4, we get this gap in the robin egg blue. That's our hydrogen bomb or beta line I mentioned. Doesn't even happen down here. Why would that be? Well, on these cooler stars, let's start with the really hot ones. Oh, went a little far. On these cooler stars, when the electrons are heated up, they jump, they're so hot, they go right past level 4 to 5 and beyond. So not as many electrons stop at 4. And so there aren't as many absorptions here. And on these cooler stars, a lot of the electrons don't get pumped up beyond level 3. So they're not even making it up here to create that line. That's why these are dim and these are even, there's no line at all. So now, you know, my wife, she's always talking about dressing for success for me. This is, I don't think this is exactly what she had in mind. In fact, I know it's not what she had in mind because she's told me that on more than one occasion. So, but this is the perfect slide, right? You have all those colors on the slide, and there's your hydrogen alpha in there. And, you know, that's just the way things go. And I'll tell you that we've had a little problem here this last 11 or 12 months because down here at the bottom, they're no longer red. They're sort of gray, and we're all about color in spectroscopy. My salon's been closed. They're not picking up the phone. I can't get appointments. I'm not going out anyway. I've had my first vaccination, but not the second yet. So I know some of you probably had similar experiences in your homes. So you see that crosshair there? There's a little bit of dimming in the robin egg blue there. Now, if I was to do, maybe I got some time on a Hubble Space Telescope and I captured a spectrum and I wrote an article and I said, there was a little dimming in that robin egg blue. Would that get published? No, it's not science. It's too qualitative. In order to be quantitative, we have to measure these numerically somehow. And we do that with a graph. This is an intensity graph. So this axis here is intensity. So the star is really bright. And so this peak is really high. The star is narrow, so this peak is narrow. Whereas this thing is what, dim out here and dim out there, but pretty bright in the middle. So it starts dim, gets brighter, 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 dimmer, dimmer, dimmer. And watch this. That dip right there is an absorption line. That's the hydrogen bomber line. Now we can do science. Now we can measure where is that line, what color, how deep is it? Well, where is it? It's in the robin egg blue. But how deep is it? How's it compare to other stars or other friends' telescopes? So how do we get this graph? So my story is in 2009, I got one of these gratings because I wanted to do some spectroscopy. I went outside in my backyard right here, right outside that window with my C8. I'm 3 miles from Pike Place Market. And God, there's things showing here that I'm supposed to show. So I went out at midnight one Saturday night. I was looking at Vega. I came in a few hours later. I had some video that I'd shot with a Logitech webcam. And I just put the grating, I took the barrel off an eyepiece and duct taped it onto the camera globe sphere. And, my blue jeans, my knees had grass stains because I was kneeling, it's Vega overhead in the summer. So the next morning, Sunday morning, I wanted to take this, and this is a frame from that first video, and create this graph. So I downloaded some freeware that was out there, and about 2 hours later, I quit. Maybe 3. Maybe I'll give myself the benefit of the doubt. The problem was the software kept crashing. It was half in French, half in English. It just wasn't designed to the level of usability and quality that we've become, all of us, accustomed to. And I told my wife, I got this grading because I wanted to have fun. This is a hobby, and I'm not having fun. And I threw the grading in the drawer. But it kept bugging me over the next couple of weeks, and I decided, okay, next Saturday, I'm going to spend the day. I've been developing software for many decades. And I'll write something to create this graph off of this colorful but qualitative image. So Sunday morning I was done, and now, 10 or 15,000 hours later, the software is almost finished. My wife keeps saying, would you finish the software so we could have dinner at a decent hour? And it's done. It's been done for a while. And this is definitely a ding moment, because I think all of us, including me, when we think about getting into something new, part of us goes, oh no, another piece of software I'm going to have to learn. And I felt that way too. So the software is designed so it's not that way. And I want to spend just 2 minutes. Look, I know it's the evening there. Many of you have had dinner. If I get into a big software demo and your video's on, I'm going to start seeing the tops of your heads. And if you're not muted, I'll hear you snoring. So, but I do want to show you how easy it is. This is the software here. This is a frame from a paused video. It could be a FITS image that got loaded. It could be, most any camera feeds it, as I mentioned earlier. Here is the star. There is the spectrum. Notice there's a gap you can barely see there, and it looks like maybe there's some in there. So all you do is bracket in the region that you want to study, and over here you get that intensity graph. So this peak here is because the star is very bright over here. And then this data is this. And so that dip is that dip right there. So big deal. So we got some dips. What's it mean? Remember I mentioned that Bunsen, when he burnt all those elements and kept great records, well, those records, that catalog he created, the grand catalog is still used today, and it's embedded in the software. So I can come up here and say to the software, show me on this graph, when I check this box, where there should be absorptions if there's hydrogen on that star absorbing starlight as it leaves the star. And look, we've got a match there, there, and there, and maybe a couple there. So now with an 8-inch Celestron 8-inch telescope, a Logitech webcam, first time out, not a big imager, that's me, not a big imager, I was able to detect the absorption from a distant star because of the gases absorbing light as those electrons jumped around. That's how easy it is. And there's 2 other quick things to show you here. One is to show you that I'm going to play this video here. Let's just start it playing, and you'll see it jumping around a little here, and you'll see it jumping around here because our seeing is changing, right? Now, built into the software is some stacking. So you see that dip there? Let's turn off that fill. There's a dip there. I'm just going to turn on stacking for a moment. It's going to combine images, just average them. We're playing at 2 frames a second. Watch how quickly that barely discernible dip becomes relatively smooth, relatively symmetrical. I love that real-time demo of what stacking is all about. Okay, so I'm going to stop this. And the last thing I'd like you to just keep in mind here, in your mind's eye, if you would remember that region, because, and what I want you to remember, if you would, is just that I had here some reference lines for hydrogen alpha. There's that hydrogen beta in robin egg blue. So these dips, we're going to see how, using these lines, we can do science. as we continue on here. So let's come back to the PowerPoint show. Here's an example. For example, I know some of you do outreach, whether it's at the observatory or in the city. This is the kind of thing that you can do in outreach. The colors really interest people. This is a gas tube they're looking at, but then they look at the star. This is a ding moment also, because unlike astronomical imaging, you can do spectroscopy even if there's a lot of light pollution. See, we're not interested in all of those sensitive balances and details that visual imaging is really concerned with in order to get good images. So all we need to do is find those dips. So it's something you don't have to schlep out to the observatory or somewhere else. Maybe go to Florida for the Winter Star Party. You can do this kind of thing in your own driveway. And in fact, when I'm done my talk, I'd love to hear from people with the blackouts, the rolling blackouts there, outages, whether you're seeing any more of the sky. I know in New York City during a big blackout in the 60s, they could see the Milky Way. So here's a image of 3 stars. There's their spectra. There's some gaps. Here's a star there. There's some lumps, you know. So I don't think that's a technical term. But those are emission features that have saturated our sensor. In fact, let's look at one of these. So when Janet Simpson sent me this, really a confession here. I couldn't remember what a Wolf-Rayet star was. She told me that's what it was. Wikipedia is our friend, thank goodness, because I'd read about Wolf-Rayet stars over the years, but typically things go in one ear and out the other. You know what that's all about, right? So Wolf-Rayet stars are late-stage stars that have dissipated some of their outer shell, and we can see down into the star, very intense stellar winds. Let's look at the spectrum. So this bright area showed up as this peak. It's carbon, carbon, carbon. Why would we be seeing carbon on a star? Well, remember, stars burn through their elements, starting with hydrogen to helium, and carbon along the way is one of the elements that they're burning. And we're actually seeing it here in the star. Pretty amazing. So these are emission spectra because they're bright areas. Let's look at another emission object, our beloved ring nebula. There it is. And you can see 2 elements there, hydrogen alpha, and this O for oxygen, and then that 3 means ionized. It just means some electrons have been pulled out. Most extended objects, as opposed to point source, are pretty boring in this grading because it doesn't have a slit. That's why it's so inexpensive. In order to look at extended objects, we need a slit device like these. You can see they're considerably more expensive. They're like an order of magnitude more expensive. And they're much harder to use because now we have a 20 micron slit that we're trying to acquire our target and track on. Nobody really starts with these. They start with a grading, and then over a couple of years, maybe they get comfortable and committed enough that they are willing to spend that money. So here's the Orion Nebula with a slit spectrometer. Look, there's hydrogen alpha, nice narrow peak. There's that ionized, right? That Roman numeral 3 oxygen, nice narrow peak. Pretty cool, huh? So I'm going to stop sharing for one moment here because I thought it would be fun. If anybody wants to, I won't certainly call on anybody. If for somebody to share their first experience seeing the Orion Nebula. Where were you? What did it look like? Is anybody interested? You can just unmute yourself. Feel free. Bueller, anyone? Anyone?
I got
Go
one
ahead,
actually.
Thank you.
Just a couple years ago, actually, when I joined the astronomy club, I actually got a 10-inch Meade Lightbridge telescope, and that was the first time I'd ever even tried to look at the Orion Nebula out at Mounds. And I just thought, oh, it's just going to be a fuzzy blob. I'm not going to see any detail. And then you could see the whole structure. It's like, holy crap, that's been up there this whole time, my whole life. Yeah. And I never saw it. And so really, now every time somebody's every time I get a chance to show somebody, it's like, you got to see this. You've never seen this before. Nerd, but you're amongst your people here. And that's a great story. And I've never really heard it described that way, but you're right. You know, it's always been there for us to see. It was back during the time of the Egyptians and the Romans. It's always been sitting up there waiting for us to see it. So I love that story. That's a great one. So my experience was similar to yours, except the telescope wasn't quite up to it. It was in the early 90s. Shoemaker-Levy 9 was coming. I thought, gee, it'd be fun to do some astronomy. I never had. I'd seen pretty pictures in the magazine.
So I went to the Denver Astronomical Society Urban First Quarter Star Party. And you know, it's fun when you can remember before you knew something, how wrong you can be. And in this case, I certainly did. So I got out of the car. There was a little berm that I had to step over. Remember, this is in downtown Seattle. And what I saw to my uneducated eyes, you know those cannons that they shoot people out of in the circus? That's what I thought I was seeing. I was really confused. It's like, what's going on here? Why are they here? Of course, they were doves. I know better now. I walked down to the observing field. There was somebody much like many of you or me running the Dob. They were looking at M42. I queued up. I got to the eyepiece. And unlike Brian, I was really let down because it was the fuzzy blob that you didn't see, Brian. And I went, WTF, what's the deal? This is, why bother? But I really wanted to do it and I stuck with it. And of course, these days, many of us do look at M42. And many of us may have had a similar experience to mine when we started. Why would we go out again to look at a fuzzy blob? Well, of course, we've got dark sky sites, we've got better telescopes, and we know, of course, how to use averted vision to really, see things out of the corner of our vision. So the key, though, all joking aside, and this really is a ding moment, and that is when we understand what we're looking at, whether it's visually, whether it's imaging, whether it's spectroscopically, when we understand what we're looking at, the experience gets that much more rich. And now we all know that it's a stellar nursery, it's the birthplace of stars, and that makes all the difference. And for me, the ding moment is that I've learned a lot in spectroscopy that has deepened my experience in other areas of astronomy, including just my reading. And so I understand a little bit more about how we've come to know what we know in the field. They say like 80% of the astronomical research that gets done with spectrum. So let's look at that spectrum, those pair of spectra up there, deep, wide absorption features, right? So we've got some bands. What do we know about bands? Well, bands are when things are cool and there's a complex molecule that can create all those lines. What would we be seeing that was a complex molecule on these cool planets? Well, we're seeing the methane. We're actually detecting the methane. Again, this is Torsten Hansen again with his 8-inch video. So this is how, of course, one of the ways that we'll discover an ET someday, hopefully, is we'll see evidence of processes that create molecules that have a very short lifespan. And we'll go, hey, if we're seeing them now, it's likely they were recently produced. Anyway, so in 1881, Henry Draper observed a comet, and the New York Times thought it was an important enough event to write this article on it. So here, down here, we can see the spectrum of a comet. At the bottom, you can see it was just done with a DSLR and a small refractor. Somebody's mic is on, Brian. Maybe you can mute again.
Oh, sorry.
No problem. Over here, we can see the intensity peaks. These are called the Swan Bands. Now, this was captured by a guy from India named Vikrant Agnihotri. He's a nuclear power plant engineer. This was 2013. He was a beginner. Now he's really advanced. He knows a lot more about it, both theoretically and practically, than I do. And what teacher doesn't like to see their student surpass them? And he's done that. I spend a fair amount of time, I wouldn't say teaching, but helping guys and women learn the field. And it's one of the joys that I get is being able to share the joy of discovery that a new customer gets the first time they capture a spectra. It's electrifying. So here is a little bit more recently, Neil Wise, you can see. We can see some sodium in its bands. So this slide, anybody who uses a C-clamp, that's my kind of amateur observer. The problem is, if I break everything. If I was being the one with this, I'd like just tighten down that C-clamp and probably collapse the housing of that video camera. Fortunately, Robin Leadbeater isn't all thumbs like me. He attached a star analyzer grating. He's a designer of it, actually. And he observed the Perseids. And down here in one of the frames, he caught the movement of a meteor. And over here is the spectrum, this thing. And that gap right there is that dip. Now, this is a really rarefied area. This is like a niche in a niche, right? You got to wait for the Perseid and, but, whatever turns you on. And some people like doing this kind of thing. So we won't talk much about the sun right now, except to point out that in 1868, these two saw that yellow line and they went to Bunsen's catalog from about 10 years previous. And Bunsen had never burnt anything that had a yellow line right at that wavelength. They didn't know what it was. They gave it a name. Helios is the name in Greek for sun, so they called it helium. Now, fast forward 40 years, some researchers were burning a gas they had here on Earth, and they looked at it in a prism in a spectrometer, and they saw the same yellow. And they were able to go, that helium stuff about which we knew nothing except it glowed at this wavelength when it was burnt, we've now found here on Earth. I love the example of how science works, that we can discover physical properties of objects that are millions of miles away. So if you're into novae, there's some that have iron absorption lines that you can capture on a DSLR, some don't. So just a quick review for Doppler shift. It's the change in pitch that something goes through as it's coming towards or away from you. So the classic example most of you may be familiar with is a train coming through a station with the whistle on. It's high as it's coming towards you, low as it's going away, high, low. Same thing happens to light. There's the low when it's as it's stretched out, and there's the high when you're coming towards it. But here's the example. Suppose we were expecting to find this triplet. I love that term. It's almost self-defining. Expecting to find this triplet here, and instead we found it over here. We would know that that light was coming from an object that was moving away from us. It was redshifted, like the train whistle. And if instead of over here, we found these lines over here, we know that that object was coming towards us because it was blue shifted, shifted towards the blue. Let's look at a cool example. So when stars explode, sometimes they're called supernovae. And I'm not going to get into the details here, except one particular kind of supernova is a type 1a. When you have a big star and a small star, and somehow some of the gas from this ends up on that, when you pour gas on a star or on a hot surface, what happens? It explodes, right? Let's look at an example here in M101. There's the supernova. There's what a type 1a supernova would look like. Not this one, but you can see it's not just a point anymore. It's actually this expanding explosion. Well, there's the spectrum captured by David Strange with a 9-inch telescope in less than 20 minutes of imaging time. So there's the spectrum intensity graph. So that little darkness there shows up as that deep dip. We hear a lot, and rightly so, that we stand on the shoulders of giants. And I thought about that the other day, 3 weeks ago, when I got my first vaccination for COVID. And I said to this doctor, I said, the history of humanities science research, starting hundreds of years ago, if not thousands, so much was learned, so many false paths went down, positive paths went down, eventually came to this injection in that syringe was the fruit. I love the expression fruit. It was the fruit of the giants' work over generations and generations. Well, the giants also have studied these supernovae, and they have determined that when there's a deep dip right here, that's the signature of that supernova that is going like this. It's not, there's other types of supernova where stars end. One is core collapse. They run out of fuel, they collapse. So here's the spectrum of a type 1a supernova. There's that deep dip right around 6,000, that's silicon. Notice that these core collapse supernovae don't have that dip. So the giants figured out how to use a spectrum to tell the type of supernova that we're witnessing. So now this is pretty cool. We measured, David and I looked and found that this dip was like a 6150. Now stick with me real quickly here. So that's what we measured in the graph below. And now if Bunsen had burnt silicon beach sand, he would have seen that dip at that wavelength. Now, I don't remember the Doppler shift formula. I didn't at the time either, but Wikipedia is your friend, as I mentioned, and we are able to calculate the blue shift. It's actually shifted and the radial velocity as that shell is expanding towards us at 22 million miles per hour. And we did this with a backyard telescope. Isn't that remarkable? So Adam Rees and his team, you may recall, won the Nobel Prize in 2011 for work that they did just before the turn of the century, where they studied the accelerating cosmological expansion. And guess what type of star they used as a standard candle? Type 1a supernovae. Somehow, I think his equipment was a little more sophisticated than this here. But it's fun and really pretty exciting. Not only can we do it, but the professionals want our help in classifying these. Because, you know, what we bring to the table, just like the AVSO and photometry, and now they're doing spectroscopy, is we can do these time series and really see changes. You can't get a lot of, professionals can't get a lot of time on these expensive telescopes. We can get a lot of time on our telescopes, and they want us to help classify these. Unfortunately, they're often very dim, but again, it's something we can do. What about the spectrum of a black hole? Well, a black hole wouldn't have any light escaping it, right? So there wouldn't be a spectrum on the black hole, but the accretion disk of that matter spiraling into the black hole gets very hot and creates a spectrum. So David Hayworth captured the spectrum of this quasar 3C273. There it is over on the right. You can see two little points of light. Let's zoom in. There they are, and there's the graph. So now I don't know if she's still with us, Ruby and your brother Abe, I think it is. So this guy wasn't much older than you are today when he made this discovery. I mean, to you it may seem he's a lot older. He was like 25 in the 1960s, but pretty young compared to most of the people who are in this meeting, I'll tell you that. He stared at this spectrum and he wanted to know what those peaks and dips were. So he did what a lot of scientists do. He said, let me compare an unknown thing, this, to a known thing and see if they match. So he looked, this is that screen from my software I wanted you to keep in your mind's eye if possible. There's where the hydrogen bomber lines, there's that hydrogen beta in robin egg blue. And he looked for matches. He went, oh, these lines here don't match these lines from 3C273. We know they're not, these aren't hydrogen since they don't match. Except they were. They were all the right distance apart, but they were shifted over to the right. And that shifting indicated that this object was moving away from us so quickly that it was billions of light years away. It's a long way away. And I think one of the things that we all enjoy, especially when we get out to dark sky sites, is that canopy of stars and just appreciating the enormity of the universe, how big it is. Sometimes it makes us feel small, other times it just makes us feel good. Mostly the good, I hope. And there's two examples. I mean, all of us have had our examples that we've liked over the years. Two examples with this quasar. If it's as far away as it is, for us to be able to see it, it had to be as bright as 100 times all of the stars in the Milky Way. And I don't know how far away the star Pollux is, but I know it's far away. And this quasar, if it was at where Pollux is, that distance, it would be as bright as our sun. That to me is mind-blowing. So the thing that amazes me is this light took 2 billion light years, right, to come to us. A long way, a long time. And yet it still has information in it that we can tease out something about that object as it existed billions of years ago. It's like that light didn't age, right? Well, people age. This is, of course, Martin Schmidt in the 60s, as I mentioned. There he is a few years ago. Now, people have justly accused me of throwing him under the bus with this pair of slides, but yeah, listen, he's got a full head of hair. I'm envious of the guy. Give me a break. Two more quick examples and we'll finish up, okay? So the first example here, this is what we've been looking at, these bomber lines, the alpha, beta, and they're about 50 angstroms across. That's about the limit that we can see. Suppose we want to look at detail in that feature. Well, wouldn't it be nice if we could just take our mouse roller wheel and just roll in? Unfortunately, we can't. You know, that would be like, you know, when you're looking at the moon and you want to see more detail in that crater. Early on in a lot of our telescope careers, we just got a higher magnification eyepiece, right? But eventually you get to the point where it's empty magnification. We just, with that equipment, can't get any more detail. And the same thing goes with zooming with the mouse. In fact, in order to zoom in and look at the detail of this hydrogen alpha feature, we need to use one of those expensive slit devices I mentioned earlier. Quick example of how they work. Here's Vega. You can see a nice dip here. That's a known. Let's compare Vega to the moon. The moon's not really moving towards or away from us. And look how those are offset. There is Doppler shift. We've now measured the radial velocity of Vega that's shifting the color of light like the train whistle gets shifted as it's coming towards or away from us. So, but like I said, this takes expensive equipment because now we're down around 0.67 angstroms. There's just no way we'd be able to get that kind of detail on this timeline. Okay, final example. I've got a visual aid here. I thought I had, oh, here it is. Climb under the desk, hopefully not bumping my head. This is a rotating star. Now, if you think about the light that's coming off of that star towards you, the light from this edge has some Doppler shift. It's blue shifted, right? Because the edge is coming towards you, right? You see that, Baron? That edge is coming towards you. Whereas this edge is moving away from you. So this light is blue shifted. So we have both blue and red shift. Here diagrammatically, let me show you what that looks like. It's spinning like that. And this light is blue shifted because that edge is coming towards us and this edge is red shifted. So instead of a nice sharp peak like we get on Vega, we get this broadened peak because some of this light has been smeared to either side by those two shifts. The giants really were giants. Imagine, just with a rainbow, we can study and learn how fast a distant star is spinning. So to finish up, how do you get started? Well, I mentioned the star analyzer grading is it's about it's $195, not 200. You need some sort of camera, almost any camera. If you're using a DSLR on your telescope today, it's easy just to thread this on to the telescope T-ring with an adapter that we've got. You need some sort of software. Now, RSpec is the name of my site, as well as the software. The R stands for real time, because I love going out, like I mentioned, with a video camera. And by the way, you know, if you've got a video camera and you're showing this graph and it's colorful and it's jumping around a little bit, that is a huge winner, as I mentioned earlier, for star parties. And that is a ding moment, because this can augment your current star parties. You don't have to know a lot to be able to discuss with people what they're seeing. And I think you'll be surprised at how fascinated people are. Many of them have heard about spectroscopy in the 3rd or 4th episode of Neil deGrasse Tyson's Cosmos series, the remake. So this is the software I mentioned that I tried first. I'm friends with both the authors, both from France. Very powerful software. It's difficult to use. They're not professional software developers. And you may need, final thing here, you may need a little spacer between the grading and the camera. And that's because this distance, it's not critical. It's not like focus, but it needs to be in a certain range. And I've got on my site a page where you fill in your setup. And if you get 3 green flags over here, that means you're good to go. A lot of people just send me the specs for their telescope setup and camera, and I just figure it out for them. It's a little bit of a speed bump getting started. There's tons of great books out there. On my site, on this links page, is a discussion of a really cool book. In fact, there you can see one of the pages, and look how, I mean, it shows you that here's everything you're going to see. But listen, like I said, I'm not an astrophysicist. I don't know the significance of helium versus oxygen. But this book, it's the same book that the page on the screen shows is from, has all this great text that explains what we're seeing. And the cool thing is, it's written for people like you and me. It's not written for postdoc astrophysicists or grad students or undergraduate astronomy majors. It's written for amateurs. It's a great book. There's a lot of books linked to on my site that can be helpful. I've got we've got a forum here that has a lot of people like me who love spectroscopy and love helping people. The AVSO has jumped into spectroscopy pretty deeply in the last 3 or 4 years. About 3 or 4 years ago, I gave a presentation at the SAS conference in LA. It was actually a hands-on workshop for 100 attendees from the AVSO at their meeting. You can now download the sample data from that workshop. My software is free for 30 days, and you can watch a YouTube video of that workshop that we made. So even if you never plan to do this yourself, tomorrow morning, if you've got power, you could, and it's warm enough to operate a mouse, you could actually go through that workshop step by step with our data. And when you were done, you'd really, in your bones, you'd have a good appreciation for how spectroscopy is done. There are opportunities for professional observations. Every one of these names on the top row here are amateurs. The AVSO has a spectra database that they're building now and is becoming a useful tool for professionals. So in the last 200 or 300 years, as well as in the last 45, 50 minutes, we've come a long way. I'd like to thank you all for your attention tonight, for smiling at a few of my jokes. I'd like to also make a special point of thanking those of you who are doing outreach. Of course, it's one of the ways we can pay it backwards as well as pay it forwards. It's so nourishing, as you who do it know. So I'd like to thank you for all doing that. We've all been so privileged. How do we know that? Because we're here today watching a show like this. We have the background, the understanding, the food in our stomachs. We really, those privileges, not everybody has, and so giving back is a way to extend our thanks to those people. I love questions, whether they're now or whether they're at some other time. Feel free, there's a contact form on the site, or you can send me a direct email. And I'll help you get started if you want. Even if you're not planning to get started, if you've got questions, here's your chance now or via those URLs to chat with me. So thank you again very much.
Okay, do we have Q&A time?
Yeah, so any questions from the group?
If one was, oh, go ahead.
Go ahead, Brad.
I just wanted to let everybody know that I have had a chance to use this software. I didn't use it with my own equipment. I used it with the telescope in Perth, which unfortunately is broken. So I wasn't able to do too much with it. I was kind of just learning to use the equipment and software when it broke. But I can tell you that my experience with it was, I'd also tried ISIS and BSpec, and Tom is exactly right. They are very difficult to use. His product is much easier to use. I'd say not only does it seem to be more user-friendly, but it's just got so much more information behind it, so many more tutorials. I've heard from the guys who ran the scope in Perth that he's helped them a lot. So that kind of, I didn't ever actually communicate with him, but that does tell me that he is there to support his product, and hopefully I'll be able to get back to using that at some point.
Great, Brad, thanks so much. You followed the script I sent you before the meeting pretty well.
Yeah, I'll need that check.
It's in the mail. So any other questions? There were a couple others. John, did you have one?
Wasn't me.
Oh, okay.
I had one.
Yeah.
I own your software and your grading, and I've had some fun with it. My camera needs to be replaced. For public outreach, do you recommend the color or the black and white? I know the black and white gives you higher quality, but does it translate at all or help at all for public? Is color the way to go?
No, that's a really good question. I forgot to mention that. For outreach, color is definitely the way to go. Otherwise, we get that smudge that Brian and I were talking about earlier. You know, we really, when people see a Roy G. Biv rainbow, that's interesting to them. But as you anticipate, the smudge doesn't have the punch. You'll be able to, image, you only need a couple stars in outreach. In fact, only one. You just image Vega and you're good to go. So it's a good question. I appreciate you asking it. Color is the way to go. And frankly, it's not that inferior to mono. Thanks for asking that. It's a good question. Other question.
My other question, though, I came across where I struggled is, okay, I'm getting good data. I've got these great graphs. But is there any community out there that can actually use this data in a more scientific manner? Like, are Is there a place where you can look up, okay, I need data on this star at this exact moment, you know, outreach or anything?
Yeah, that's a good question. First, the AVSO brought up their database online last year. And they're, you know, Stella Kafka is their current great executive director, and Arnie before her. They're professional astronomers, and they understand the importance and the fact that spectroscopy is so key to what we know today. So their database is beginning to become populated. There are professionals who are using that data now. Yours is a good question. I think all of us would like to feel we're contributing to the advancement of the field, you know, and helping the giants understand things. So the other place that you can go is there's a place for, who's the supernova hunter? Tim Puckett. He showed at one of the SAS conferences, he showed a screen filled with supernovae that the professionals were hoping that amateurs could classify. And so that's an opportunity. Right now, there's no cues of I need this or I need that in other areas, but we're getting there. That's a good question. I'm glad you're using the software and feel comfortable that you can produce usable data, because you can. That's what I'm stunned even now, 11 or 12 years later from when I started, that this is possible at all. I think, and that's maybe the most key ding moment of everything. And that is, we can actually do this. It just blows my mind. Anyway.
Well, yeah, my goal is I want to eventually be able to show my daughter the expansion rate of the universe with the equipment in the backyard.
Perfect. Yep. And the colors she'll get a kick out of. She really will. And this is the kind of thing, frankly, you know, I know some of you do outreach today, but the amount of sort of science that we can do with our outreach is fairly limited to the moon, Saturn, and Jupiter, you know, by the overhead lights at the football field at the high school. That's about as far as we can go. But I think once you've gotten comfortable with this, as you two have, and others also, it's another tool in your toolkit. You can actually go into a high school, talk to a chemistry teacher, talk to a physics teacher, or if they have an astronomy teacher, talk to them and say, I can show your students spectra. Chemistry teachers love this because spectra and these shells with electrons jumping around is the name of the game in chemistry, right? Physics teachers too. Now, again, wearing my sales hat for just an instant, if you were to go down that route, you might find that a camera like this and a gas tube, and many educators have those already, in the classroom allows you to, and you could put together a song and dance where you went in, you know, once a year to 5, 6, 20 classes and gave a little demo. You wouldn't have to be a great speaker. The main thing is educators love this kind of outside presentation. So whether it's in your backyard, as you mentioned, or whether it's in a classroom, this is something that people will learn from, definitely. Thanks for asking that question. Other questions?
Got a question. I've got one of these little Revolution Imager video cameras. It's a Malin Cam Mini, I think they say.
Yeah.
Those low resolution cameras, or will they work, or you need something more higher?
No, they would work. I have several people who have talked to me over the years about using the Revolution Imager with the Star Analyzer grading. And Malin cams also. You don't need a high-end cooled camera. Look, you know, as I mentioned, that first night out, I have it here somewhere. It's got all the duct tape all over it still. It was one of those Logitech webcams, and in those days were like looked like a billiard ball almost.
Yeah.
I mean, it was nothing. And you'll see examples on my site. That's the other thing, just for you to check out at my site is, and let me show you that screen because it's fun to see. On the site are some examples under samples of different kinds of things you can do. Some of these you may recognize from my presentation this evening, but there are lots of kinds of things that you can do. This here was done with just a webcam. This is the redshift of a galaxy, done with an 8-inch telescope and just a webcam. So the cameras you've got may be sufficient, maybe not for a galaxy because these are probably longer exposures, but bright stars, not a problem. So if that's a road that you decide you want to go down, you can use our contact form on the site, and we'll make sure everything fits together and that it's going to work for you the way you want it to. Other
Does your,
questions? Yes.
does your software have that comparisons spectra built in like the Vega one versus
Yes. Yeah, that's one of the great things is that all the data that you're going to need for common objects that might take you years to observe is in the software. Plus, with the forum, you can get online and say, I observed this thing. I haven't really been able to learn much about it. I read about it in a book. Or could I observe this thing? I read about it in a book. What do you all think? And it's really surprising community. Everybody, I think perhaps because we're a small group and it's a niche, we're all, I never know whether it's niche or niche. I've heard it pronounced both ways. I think everybody is very supportive of one another, and you'll find data and understanding of what's going on. Again, I want to emphasize the science is the kind of thing that you can spend a lifetime learning, but you need not in order to have a lot of fun. Other questions? Thanks for that, John.
Yeah, there have been several questions posted to the chat.
Oh, okay. Let me pull that up. I didn't have that up. There is not, to Robin, there is not a 2-inch format grading, but there is you can get from a variety of places. Aegeus has one, a little 2-inch to 1.25-inch thread adapter. One thing is, it'd be great to have a 2-inch grading. They're really expensive to produce because of the defects that happen. Much like computer chips, that many of which get thrown away because they have a defect. Same thing with the gratings. But we don't really need the full 2-inch, even though there'll be some vignetting. We're mainly interested in the star, and put the star in the center of the field of view, and we're good to go. The advantages and disadvantages Robin asked of CMOS versus CCD are the same traditional advantages and disadvantages. And I'll be quite frank, I don't know a lot more about that. That's the kind of thing you could ask on our forum, and you'd have people who would be only too happy to discuss those with you. I know that some of the more modern cameras people are now using with the star analyzer and slit spectrometer. So it's not like, oh my God, we're not going to be able to get cameras that work once these take over. That's not going to be the case. Thanks for those questions. Anything else?
Let's see, somebody asked you.
Oh, go, John.
Go ahead,
I want to ask your website, and you put it in the chat, but can you tell them what it is?
Sure. Website is rspec-astro.com. And I'll pop it up on the screen there just so you can see it. And there it is. And you'll find, one of the things about, as I mentioned earlier, learning software isn't something most of us enjoy. Once we know it, we love it, perhaps. But this software doesn't come with a big, thick manual that you have to spend weeks reading. You'll see on the site there are tutorial videos that are 2, 3, 4 minutes long. And it's like I'm just sitting there showing you something that you'd like to understand how to do. And you work your way through those videos. You can look at them tonight or tomorrow, whenever. And they're open to the public. And they'll explain a lot about how this gets done. And those are all on the site. As you explore the site, I think you'll see some really helpful videos to give you an idea what this is about. Well, listen, I'd like to thank all of you for your time today. Oh, yeah, go ahead, Craig.
If I could intrude once,
Please.
when you were talking about the, actually, can I share my screen?
Please, go if it's enabled for that, sure.
Let me, if I can, real quick. You mentioned is that showing?
It's coming. Give it a moment.
You mentioned the discovery of helium. That actually was discovered about 70 miles from here in a little place called Dexter, Kansas.
Wait, I got to get a screen capture of that. That's wonderful.
They drilled a gas well, and they lit it and it didn't burn. And they didn't know why. And so they tried to figure it out, and they actually discovered it was helium. And so if you're on your way to the Cosmosphere, that's a space museum in Hutchinson, Kansas.
That's very
Taking the back roads, you come across this sign about the gas that wouldn't burn in Dexter, Kansas.
Wow. And I'm seeing there in the first paragraph, it was called scrumfully wind gas. My wife would classify wind gas as something else that happens. while
Yeah.
we're on TV.
Yeah, well, it wouldn't burn. It kept blowing out the flame. So it was pretty funny.
Really something. That's great. Thank you for sharing that. When you said
Yeah.
you wanted to share your screen, I sort of got a little nervous. I was thinking, what's this going to be? But that was
Yeah,
really
well,
worth it. I'm glad you
No,
did.
I thought you'd get a kick out of it. I actually saw you give this talk at the Kalamazoo meeting back in November.
Oh,
And,
okay.
I thought
Wonderful.
about mentioning it then, but I wasn't a member then, and I didn't want to ruin their meeting with stupid trivia.
Well, I'm
but
glad you mentioned it.
Now I feel like I can do that with the Tulsa group.
Yeah, the fact that you've seen me talk twice, fortunately, there's been some time since when you first saw me, because it's like when you see a comedian do a routine, and
I could tell the wear and tear on the wig.
yeah, the wig is starting to fade, and some of those
Just kidding.
and there are air quotes here, some of those spontaneous asides that I made, you may recall from 4 months ago when you heard me talk. So sometimes things, whether it's a stand-up comedian, I try and get you to laugh. And those of you who had your video on, when I get a laugh, I know, I mean, look, I like making people laugh, but more than that, I think it must release chemicals in the brain that help us relax.
Okay, I'm laughing.
There we go. Now you got your video on. I can see you. Good. Well, thanks again. I appreciate that you came again for another dose.
Yeah, it was great. I enjoyed it both times. So the encore was, in fact, I think I did enjoyed it better because I had a little more understanding of it.
Great.
So thank you.
I'm glad to hear it. And Robin just asked, does the software work with just FITS files or other formats too? It will work with bitmaps, JPEGs, TIFF files, most of the common formats. I hope that answers your question, Robin. If there's a specific format you're interested in, let me know. Otherwise, it sounds like if you're using a specialized format, maybe you have the tools, oh good, to convert it into FITS. I see that answers it for you. Good. All right. Well, listen, gentlemen and ladies, it's it's 8:30 there and it's 6:30 or dinner time here. So I'm going to head up and upstairs from my man cave that you can see in the background here. Thanks again. Take care. Stay safe. Get those vaccinations. And don't forget that outreach. You're welcome, Baron. Thank you. And have a great evening. I'll leave. Now you can talk behind my back and really talk about what you thought of my sideshow here. See you guys later. Thank you, John.
Thank you very much. Everybody enjoyed it.
Thank you.
Good. Yeah, see you, Denny. Good night, Brian. Thanks for playing, Brian, with the M42. Bye.
You're very welcome.
Luke, are you and Ruby still on? Yes. Luke and Ruby, are you still on? I guess not. Brad?
Yes,
Can you
sir.
tell us a little more about the geosats?
Sure. If there is going to be an article, I think John has it now in the newsletter. It should come out before March 6th. March 6th is both our, I don't remember which kind of observing night it is, but it's a Saturday night. It's either the observing night or the one after it. And it happens to be the best time. There's 2 times of the year in our latitude in Tulsa that are really good for what I'm about to talk about. One of them is in early spring and the other is in late fall. So March 6th is the best night this year. Pretty much moon free. Hopefully it'll be snow free. We'll see what happens. But I'll let you read the article to get the full story. But at those times of year, we have geostationary satellites that sit right above us. If you have Dish TV or Direct TV or anything like that, those are the satellites that broadcast your television to you and maybe your internet. At those times of year, they line up where their solar panels reflect the sun right back to us, so that even at night they light up, and they're normally pretty hard to see. I mean, they're 12th, 13th magnitude. I do imaging of them all the time, but they're really dim even on that. This is a situation where they light up so brightly that you can see them with your naked eye. The trick is to kind of know where to look, and the article describes all of that. It doesn't really get into the technical side of it too much. There's a lot of that on the internet. What I found a few years ago was I needed a guide, a practical guide for me to go out and look at them. I didn't really need anything to tell me what was happening or what they looked like when they were built. And hopefully this will do that. If you get to read the article and want to try to look at them, I hope to be out there that night. Hopefully it'll be clear. And if anybody needs any help, of course, we'll be probably still under COVID restrictions, but maybe I can shout at you what to do or whatever. Anyway, read the article if that spurs some interest. You know, these are 22,000 miles up, if I remember right. You can see that with your naked eye on occasion. We got a good chance of doing that this spring and later this fall, and just thought everybody might want to try to do that.
That's great. What's time window if it's not clear on the 6th? Is day or two either way, or is that just?
Oh yeah, either way. Of course, it's, you know, it's kind of like anything else. If you hold a mirror up to a light, if you line it up perfectly, it's bright, and if you're a little cockeyed with it, then it's not quite as bright. But probably a week before and a week after will be fine. Not clear that night.
Because we got another one on the 13th, you know, a week after. So.
Yeah, the 13th would probably still be okay. I mean, it's not, they don't just stop. It's not like an eclipse or something where they just stop shining. 13th might be pushing it just a little bit, but does anybody have any initial questions or?
I remember you showing me something out at Okie-Tex once like that. So.
Oh yeah.
In a telescope.
Yeah, it's a lot easier in the telescope. To be honest with you, it takes a little bit of effort to see and a little bit of luck in some cases to see them naked eye. But if you have any size telescope and know where to look, what happens in the field of view is if you have a clock drive, if you turn it off, the stars, of course, continue to roll along through the field of view, and the satellite just sits there and it looks like it's the one moving. They also tend to run in pairs or even little collections of 4 or 5 of them. That's pretty cool too.
Yeah. What was I going to say? Oh, Okie-Tex. For all of you listening, listened to the Oklahoma City's Club last week, and it's going to start on Friday, October the 1st, run through Saturday, October the 9th. So write that on your calendars ahead of time. They have their new building up. Walls are up. It's closed in. They said the plumbing was in. Didn't say whether the plumbing was hooked up. Hopefully it's not hooked up right now as far as water, but they're still working on electrical and some other inside stuff. But we won't have to be in that drafty tent anymore. That'll be great. So they're hoping to have Okie-Tex, which is a star party at the very tip of Oklahoma's panhandle. It's like half a mile from New Mexico in the high mesa area and some of the darkest skies on the planet. So just a heads up on that. Luke, are you and your daughter still on?
Hey, Chuck. Oh,
I see their name, but I don't hear them. So,
John, I had something else. If you're out on the 6th, the asteroid Vesta will be in opposition on it's the midnight, March 3rd and 4th, whatever that time is.
Yeah.
And it'll be a magnitude 6, kind of the once in every few years you can see it naked eye. Well, probably binocular. It's a magnitude 6, and it'll be in Leo. So it's probably worth taking a look. If you're out there on the 6th, you should be able to see it.
Very good. One other thing I forgot to tell everybody, I had a note, but I was having trouble with my computer. Bob Leeser, Bob and Judy, those of you been in club forever, know Bob and Judy. Bob has his 93rd birthday on Sunday or Saturday the 20th. So if you want to send him a birthday card, you can contact me and I'll send you his address. So Bob and Judy been in our club. They were in the club when I joined in the late 70s. So they're not quite the longest club members, but they're pretty darn close. So, you remember them, Denny?
Oh, yeah. Yep.
Is there an astronomy club out there in Arizona near you?
Which one?
In Prescott?
Oh, yeah, we've got one. Prescott
Okay.
Astronomy Club. Every population center has one. Yeah.
Good. Good. All right. Well, I thank you all for being on. If we don't have any more questions, in a few days, James will get this recorded to YouTube and we'll post it. And I'll try to remember to post the website for RSpec. And it's good to hear a couple of you have already looked at it. I saw him do a presentation a few years ago, but this one was vastly improved from that. So I tinkered around with spectra. I always enjoy taking the little fireworks glasses to our Bass Pro stuff and let the kids look at my magic glasses, I call them, and you can look at the lights there in the parking lot, and then you can look at the stars. You can see the difference between some of them have more red and some of them have more blue. But this thing would be a big step forward from my magic glasses. All right. Thank you all.
Thank
We
you, everyone.
will,
Okay.
thank you very much.
Thank
Bye.
you, John. Good to see you.
You
Good to
guys.
see you again too.
Okay.